in this virtual problem solving session, we're going to look at an axial disc clutch. We're going to look at one problem, but step through several aspects of that problem. So our problem statement, a clutch must transmit 15 horsepower at 1,725 RPM. Using the uniform wear approach, determine a suitable size and required actuating force for a single dry clutch lined with friction material, powdered metal on hard steel. Assume that the inner diameter of the clutch equals 0.577 of the outer diameter of the clutch. And I'll explain where this comes from later. I'm going to show you what this looks like in my analysis tool and what equations you should be putting into your tool. So there are three equations that should be in your analysis tool for axial disc clutches. Equation 16.3, which is the actuating force. In other words, the total normal force is a function of geometry, so big D, little d, and pressure, PA. Equation 16 for the torque as a function of maximum pressure, friction, and geometry. And then equation 1625, torque as a function of actuating force, friction, and geometry. So we're going to use these equations in different ways depending on what initial information we're given. And then I've just written them out for you from the textbook, so it's easier to just program your tool. So now let's go back to our problem and see what information we have given to figure out which equation to use. So we have information about power and speed, so we can get torque. We also have information about the material, so friction material, powdered metal on hard steel, so we could look up a coefficient of friction. Also, since we know the material type, we can get a value for PA, or the maximum amount of pressure that we want to develop on the clutch surface. So let's do that now. So here's table 16.5, friction materials for clutches. So this would go in your analysis tool. We have powdered metal on hard steel. We're going to assume we have a dry clutch because we're not given any information otherwise. So pick the coefficient of friction that's in the middle of the range. So we're going to pick 0.2 for this problem. And then the maximum amount of compression that we want to develop in the pad is 300 psi. So we're going to use equation 1624 because that matches the information we have the best. So 0.2 for our coefficient of friction, 300 psi for the pressure. I'm just going to put a 1 in here for D, and notice how my little d automatically comes out as 0.577 inches. Now, big D is not going to turn out to be 1 inch. It's just a placeholder. We're going to goal seek for that big D by inputting our value for torque. So let's go back and figure out how to determine torque. We have a clutch that's transmitting 15 horsepower at 1,725 RPM. So in my analysis tool, and I recommend this for you too, I have a section required torque from power and speed. So power, 15 horsepower, speed, 1,725. The torque that will generate is 548.05 pound-force inches. I want to show you where that comes from. So the first thing is 1 horsepower equals 550 pound-force foot per second. And then we know that power equals torque times speed, so torque equals power over speed. And then you can kind of look at how I did the conversions here. So 15 horsepower times 550 pound-force foot per second per horsepower. So that's a piece of information that you would need. 12 inches per foot over 1725 RPM, 2 pi radians per revolution, 1 minute per 60 seconds. You can see where I've crossed out the units to make sure I'm outputting units pound-force inches. So this is a good process to know. And then again, this is a good thing to put in your analysis tool. So let's remember this value, 548.05. 548.05. And now we're going to goal seek what is the big D that is going to give us a torque of 548.05. Data what if analysis goal seek set cell here. 548.05 by changing cell D. So our big D would be exactly 3.924, and then the little d, 2.264 inches. So far we've gotten big D equals 3.924 inches, and little d equals 2.264 inches. So that would be the required size of our clutch in terms of inside diameter and outside diameter, given the friction material and the assumption that we could generate the maximum pressure of 300 psi to transmit 15 horsepower at 1,725 RPM. So now I want to talk a little bit about where this assumption of little d equals 0.577 big D comes from. So we know torque is force times distance. So for a given normal force, if F is held constant, torque is going to be increased the further we are away from the axis of rotation. So the material in kind of the blue donut shape is what's going to transfer more torque. Friction material close to the center of rotation or the axis of rotation wouldn't be that helpful, so it would transmit some torque, but not as much as the friction material further away. So moving on, if you were to round big D and little d to the nearest 1/8 of an inch, what would be the new power transmitted? So in my analysis tool, kind of down at the bottom, I have equation 16.4 again. Torque is a function of max pressure, friction, and geometry, where both big D and little d are inputs. So in this case, I can override that the little d equals 0.577 of big D. So I have friction of 0.2, PA of 300. I have some old values in here. So 3.924. Let's just check that this is the right formula. 2.264. Got a little bit of rounding error because I didn't directly pull big D and little d from up above, but we are close to 548. So now I'm going to round big D and little d to the nearest 1/8 inch. So 3.924 is closer to 3.875 than it is to 4 inches. So that's what I'm going to use for big D. 3.875. And then 2.264 is closer to 2.25 inches than it is to 2.125 inches. So that's what I'll use for little d, 2.25. So then the new torque that would be transmitted be 527.7 pound-force inches. So that's just showing you how the geometry of the axial disc clutch, even when it's changed just a little bit, like rounding to the nearest standard size, can change the magnitude of the torque that's transmitted. So to recap, when we rounded to the nearest 1/8 of an inch, D became 3.875 inches and little d became 2.25 inches. And this resulted in a torque of 527.7. And then for fun, we could see what this would mean in terms of power that's to be transmitted. So we'll keep the speed the same. And now we are going to goal seek. So set C72 to 527.7 by changing the power. That makes sense. So you're transmitting a little bit less torque. Speed is held constant, so that means that you're overall transmitting a little bit less power. So power, 14.44 horsepower. And then last part of this problem, if the power to be transmitted were increased by a factor of 3, given the same speed and the same friction disk geometry. So now we'll assume, so the last part of this problem, if the power to be transmitted were increased by a factor of 3, given the same speed and the same friction disk geometry, how many surfaces would you need? So this is not a super complicated calculation. We're going to increase the power from 15, so multiply by 3 to 45. And that's going to increase the amount of torque that's required. So linearly, 1,644.14 pound-force inches. So the critical thing to remember, it's said in the book, but I just want to reiterate it here. Equation 1624. This is the torque as a function of max pressure, friction, and geometry for a single friction surface only. This also applies to equation 1625. Torque is a function of actuating force, friction, and geometry. So let's see if we're going to do our total torque divided by the output per one surface. We get 2.99999, so essentially 3. Okay, the last part of this problem is to figure out the required actuating force that would be needed given the geometry that we have to generate the pressure that we want. So in this case, 300 psi. So that's equation 1623. So we'll just use dimensions from down there just to show you that it's the same number. So we want to generate 300 psi. We would need an actuating force of 1,771.2 pound force. But then now kind of thinking about it from a real life standpoint. So let's go back to table 16.5, powdered metal on hard steel. The maximum pressure we want to have develop is 300 psi. Do we really want to induce the maximum pressure that material is said to be able to withstand? Maybe not. So we might have considered limiting our maximum pressure to 200 psi or 250 psi. And if we had done that, let's just do it for fun. So now let's say we're going to keep our coefficient of friction the same, but now let's say like 300 psi, maybe we don't want to bring the material all the way up to that pressure. So let's say we want to limit the pressure to 200 psi. If we don't change the geometry, that's not going to give us the torque that we need. So we're going to goal seek one more time. 548.05. Let me check that that was the number. So data, what if analysis, goal seek. Now we see that we need a bigger clutch. So the outer diameter about 4.5 inches and the little diameter about 2.6 inches. And then how would that change our value for actuating force? So 200. These numbers are automatically generated, so we would need an actuating force of 1,547.3 pound force. And then lastly, equation 1625 would be handy if you knew the actuating force that was going to be provided to the clutch, and you knew the material and the geometry, and then you were solving for torque. Or again, this can be used in a goal-seeking application, but 1625 just has the actuating force kind of embedded in the equation. So just a few notes about what seems to be tricky for students, and it was tricky for me as well, is that you have these 3 equations and they're just kind of like re-scrambled versions of each other. So it helps to sort of plan your problem solution before just dumping stuff into Excel and hoping for the right answer. All right, that's it for this virtual problem solving session. You will have a quiz, and thank you for watching.